So we got started on this. You guys had to pay me double, remember that? And so we had these exponential functions. And so that very first one I came up with yesterday was this one, y equals 2 to the x. We did this the other day, barely at the end of class. What I'd like to do today is plot some points and get to know this a little bit. I might have done this already, but this part might be a little bit of a review. If I plot some points for x, I'm going to plug in -3, -2, -1, 0, 1, and 2. I'd like to plot some negative values, some positive values. I just want to plug them in and work it out. Your calculator might be helpful here, but if I plug in a -3, I know how to do 2 to the -3. Because we're dealing with exponential functions, I feel like I'm reminding you of exponents. I need to remind you of some exponent rules. And so a negative exponent means 1 over 2 cubed. That's what it means. You should know that, I think. I mean, that's part of the stuff you learned before this class, but I remind you of certain stuff when you get here. Anyway, what is that? 1/8. That is a 1/8. Anyway, you don't have to know that if you just have a calculator and know how to use it correctly. Your calculator will tell you 1/8, or 0.125 is 1/8, I think. But you're right, I plotted that, I got a 1/8. What happens when you plug in a -2? It's 1/4. It's 1/4. It's a 2 squared, but it's a 2 squared in the denominator. That's what negative exponents are. That you move them into the denominator. So it's a 1 over 2 squared, it's 1/4. Hey, what about a -1? 2 to the -1. Move him in the denominator, and what do you have?
-2.
No, it ain't -2. You move him in the denominator, and he's 1 over 2 to the first. And 2 to the first is just 2. So he's a 1/2. That's a 1/2. Plug in a 0. And then this is a rule from 3rd grade. Anything to the 0 power is a 1. It's kind of a funny rule, but it's a true rule. Anything to the 0 power is a 1. Plug in a 1. Then you have 2 to the 1st power. 2 to the 1st power is 2. Plug in a 2 and you have 2 squared. 2 squared is 4. And I can plot more points, but I'm happy with this, and I want to put them on a graph because I want you guys to understand these exponential graphs. At -3, it's very tiny, man. It's 1/8. At -2, it's a little bigger. It's 1/4. At -1, it's 1/2. At 0, it's a 1. How you guys doing? You following me on that? I just plotted all those points there. When x is 1, it's a 2. And when x is 2, it's a 4. By the way, when x is 3, it's an 8. And you have what's called this beautiful exponential function. It starts off kind of slow and tight to the x-axis here. But then it just blows up. Bam! I mean, it's steep. It's very steep. I mean, we've graphed steep cubic functions and we've graphed steep parabolas, but these guys are steeper. These exponential functions are steeper. They rise quicker. And we look at a graph like that and we would call this exponential growth. Exponential growth. It has a y-intercept. What's the y-intercept? 1, 0, 1, or right, 1. The y-intercept is 1. What's the x-intercepts? Can you tell me the x-intercepts? There ain't none. I love it. You're right. There ain't none. The concept is when x gets very negative, these numbers get very small, as you can tell. When x gets negative, these numbers get small, but they don't get negative. So these y values never touch 0. You can sort of see that they're getting closer and closer and closer. They get very small, but they never touch 0. This acts like an asymptote, and therefore there are no x-intercepts. There are no x-intercepts. But there is a horizontal asymptote. it's just there. It doesn't really come from our rules. We learned rules about horizontal asymptotes, but those were for rational functions. These exponential functions come with a horizontal asymptote here at y equals 0, but it doesn't really come from those rules. It's just there. Yeah, I could ask you the domain. What's the domain of that function? You're supposed to be able to, by the way, we're at the end of this course now. Some of these questions are good because it makes you recall the beginning of this course, and we do have a final coming up in a few weeks, so asking you the domain might be a good question anyway, for review purposes. But the domain is all the x's you can plug in, and I've tried to train you when you have a graph, you just kind of look at the x-axis and what does it spread out over? And what does it spread out over? All real numbers, right? It does. It goes infinitely that way. It goes infinitely that way, but it's so steep you might not, but it does go infinitely this way. Therefore, the domain is all real numbers, negative infinity to infinity. What about the range? The range is the y values. I don't know, I might have heard somebody say greater than 1, but look, it actually gets lower than 1, but it never gets lower than 0, so it would be greater than 0. And does it ever touch 0? No, so don't include 0. So I'm just going to say y is greater than 0. And I don't want to put equal to. It doesn't ever equal 0, right? All right, so classic exponential growth function. If I walk up to you and give you a new one that looks like this, guess what? The base is different this time. You know, let me point out something. I'm sorry. Sometimes my thoughts are a little scattered. Not always. Hey, you know, what is the base of this problem? The base is this number 2. So this is a base 2 exponential function. The variable is up in the exponent. Notice when it's base 2, look at these y values. What do you multiply by every time? Every time, what do you multiply by?
1.
You can watch it. You multiply by 2, you get here. 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 Multiply by... The base is it's funny, it's the thing you multiply by every time. I mean, again, that goes back to my problem the other day. You got to double my pay. She had to pay me 1 penny, 2 pennies, 4 pennies, 8 pennies, 16 pennies, right? You had to multiply by 2 every time. So the base is the thing you multiply it by every time. That's I don't know. That's kind of interesting, I think. Anyway, so this is an exponential function. But this time I think you're multiplying by 5 every time, which I think just listen, it's the same damn thing, but I think it's steeper. Now, I don't want to plot a bunch of points, I don't, but but I'm just telling you, it's the same thing. It's probably got this asymptote here. If you did plug in a 0, what would you get? You get 1 again, 5 to the 0, anything to the 0 is a 1. So you get 1, so it's got the same y-intercept, it's got the same asymptote, it's exponential growth, so it looks the same, but it's a little steeper. So I was going to draw a separate graph, but if I drew it on this graph, he would be a little steeper. So actually, right here he would be steeper, and right here he would be a little shallower, I think. Instead of 1/2, I think he'd be 1/5 and 1/25, and so he's a little smaller here, a little steeper here. I mean, that's all. It's real subtle. That's real subtle. I mean, it's almost like I'm not going to grade that, right? I'm really just grading the shape, the y-intercept, the asymptote. The subtleness of the steepness is just something I'd like you to kind of know. I mean, how come he's different than him? Yeah, he's just a little steeper, that's all. Still good old classic exponential growth. So I think the main features of the graph that you identify are the y-intercept, the asymptote, and then you draw the shape, which is exponential growth. Listen, they're not all exponential growth. Here's another one. Watch this. I'm just going to convince you of this, maybe. Here's a different one. Y equals 2 to the negative x. When you put a negative sign up there on that exponent, maybe you remember from our days when we talked about shifting and reflecting, you know, sticking a negative sign in front of the function always flipped it upside down. You remember that. But sticking a negative sign in there for x, you remember what it did? It flipped it sideways. So that's one way you could think about this, is this thing gets flipped sideways. So guess what? If it gets flipped sideways, we don't call that exponential growth. It's not growing, it's declining. We call this guy exponential decay. Exponential decay. It's decreasing. Now you can memorize it, that it has that negative x, so it's decreasing. You could just memorize that. You could try to understand the reflection idea I just tried to discuss with you. But the other way to understand it is to plot a bunch of damn points. What happens when you plug -3 in here? Watch. When you plug -3 in here, it gets negated. See the negative sign? It makes it a +3. And what's 2 to the +3? 8. So it's not a 1/8 anymore. Are you with me? The negative sign is negating these things. If you plug in a -2, you know, over here it was a 1/4, but over here it's going to be a +2 when you plug it in, so it's going to be a 4. When you plug in a -1, it's actually a +1, so it's a 2. When you plug in a 0, what do you get? Anytime you plug in a 0, you get a 1. When you finally plug in a +1, you plug it in and it's actually -1 because of the negative sign, and 2 to the -1 is, it bothers you, doesn't it? Those negative exponents piss you off, huh? Sorry. When you got a negative exponent, it drops into the denominator and it makes it a fraction. So 2 to the -1 is 1/2. You don't have to know it. The truth is, though, you just have to be able to pick up a calculator and do it. And if you correctly, I mean, you got to type it in correctly, but it's 1/2. Are you with me? So just that little negative x made all these things kind of flip their order in any way. And if I plot these points, at -3, he's 8. At -2, he's 4. At -1, he's 2. Are you following me? He's different. He's exponential decay. Yes, ma'am.
Would there ever be a time when the lines flip on the other side, or would it always be a horizontal asymptote? It would be upside down.
Oh, if I stuck a negative sign in front of these functions, it would flip upside down, and then it would look like this.
Okay.
That'd be weird. It's possible. I don't think I'd do much of that to you. No, I'm interested in good old growth or decay. Yeah. I don't really like flipping it upside down. I do like shifting it. I might do something. I might shift it in some other ways. Watch this one. You guys ready? Watch this. This is getting. I've made it more complicated. You know, that's how things go. We add little layers, make everything a little more complicated as we go. So it's okay. Listen to this. I don't want to plot 1,000,000 points if I can help it. I did a little bit of that. You can always plot 1,000,000 points if you ever really need help understanding something. But I'd rather not plot 1,000,000 points. I'd rather just find the y-intercept. When you plug in 0, so far we keep getting a 1. But this time, when you plug in 0, you get 3 to the 0. What's 3 to the 0? It is 1. But then it's multiplied by 120. So the y-intercept is 120. So it's 120. Now let me ask you this quick question. Is it growth or decay?
Decay.
Because of why? Because of that negative x. So guess what? I'm ready to draw the damn thing. I'm ready to I'm ready to draw a decaying exponential function. And it decays and bends toward this asymptote. This asymptote is kind of always here. So that's, what am I doing? I'm thinking about the asymptote. I'm thinking about the y-intercept. And then I'm saying, is it growth or decay? And I draw it. You with me? That's important. It's growth or decay. You find the y-intercept. That's it. So this one was shifted way up. No, shifted is not the right word. Sort of stretched way up. It was multiplied by 120, and the y-intercept is different. That's good. Look at this. All right, this one's kind of funny. I'm sorry. See this guy? Let's do this guy real quick. I'm trying to sketch a quick graph. Listen, all these graphs, they're either exponential growth or exponential decay. Did you hear the difference in those noises? One of them, not. Anyway, one's growth, one's decay. That's our two options for these exponential functions, growth or decay. And I told you, when there's a positive x, it's growth. Makes sense. When it's the negative x, it's decay. That totally makes sense, but there's a funny little twist going on here. Remember this doesn't really work with the negative x, I'm sorry. But with the positive x, the base, is the thing you multiply by every time. So, when your base is bigger than 1, when you multiply by a number that's bigger than 1, your y values are going to, when you multiply by something bigger than 1, your y values are going to grow. When you but this time the base is a 1/3. So I think I'll be multiplying by a 1/3 every time. Well, when you multiply by a 1/3 every time, your y values decrease or decline. So this is actually decay. Not because of the negative x, there is no negative x, sorry, but because of the base being less than 1. So I feel like there's two ways to decay. You can decay with a little negative x up there, or, wait a minute. A base bigger than 1 with a negative x is decay, or a base that's less than 1 with a positive x is also decay. Am I confusing you? There's sort of two ways to decay. The truth is, if you know your skills, if you know your exponent rules, watch this. A 1/3 could be thought of as 3 to the negative 1. Anybody want to argue with me? A 1/3 can be thought of as 3 to the negative 1. I've tried to say that once or twice today. What's a 3 to the negative 1? A 1/3, is it? So if I rewrote this as a 3 to the negative 1 raised to the x, then I got this rule. When you have exponents raised to other exponents, you multiply those exponents. So what does this become? 3 to the negative x, which you guys would look at and say, oh yeah, that's exponential decay. You taught me that 5 minutes ago. But it's equivalent to this, which is also exponential decay, without the negative x. How you guys doing? Yeah, this plug in a 0, you get a 1, and I'm saying it's decay. Yep, looks like that. I mean, just roughly. It's exponential decay. Maybe decay. Decay means it's decreasing from left to right. It's this guy or this guy. They're the same. hey, so to summarize that, look, and then I didn't, what we're talking about kind of in general then is, watch this, I'm going to write this like this, an a times a b raised to the x. Now you didn't see too many of these with a number in front like this called a. But anyway, a is not part of the base. What's the base? The base is the thing with the exponent, and the base is b. So that's important to identify what the base is. But the a is this multiplied number in front. And we only did one example of that really. And what did it turn out to be? It turned out to be the y-intercept. That's what it'll always be the y-intercept. Well, let's just check this out. Please plug in a 0. If you plug in a 0, what's b to the 0? 1. 1 times a is a. When you plug in a 0, you get that number. So it turns out this number here is the y-intercept. Sometimes I like to think of the y-intercept as a starting value. If I'm doing a word problem, I like to think of it as a starting value. We do some word problems. Anyway, b is the base, of course. And here's, I want to say something. If b is greater than 1, no. Oh, yes. If b is greater than 1, then what?
Decay.
No, wait a minute. If it's greater than 1, like if b is a 2, or even a 1.1, or a 1.7, sometimes we have funny little bases, 1.3, 1, or 2, or 3, or 5, or 10. If the base is bigger than 1, and that's an x, this is definitely exponential growth. Right. I'm just summarizing my ideas in the mathematical notes. I know you guys love mathematical notes. How can you get exponential decay? There's sort of two ways to get exponential decay. Watch this. You could have a times b, and you could put a negative x there. As long as that b is greater than 1, that negative x is going to make this exponential decay. It is. Or you could have a times b to the x, and if that b is less than 1, if that b is a fraction between 0 and 1, then that's also exponential decay. Are you following me? These are two different ways to get exponential decay. The truth is, I don't think I mess with these fractions too much. I don't. Your homework might. I think I tend to go with, if I'm going to write a decay problem, I tend to go with that negative x. You know, I've been saying several times yesterday, the other day, and today that anything raised to the 0 is a 1. Do you need convincing of that, or you're pretty convinced? Look, I want to remind you of some rules here. You know, when you have x to the 5th times x cubed, do you know your rules of exponents? Do you know what you're supposed to do? When you multiply like bases with different exponents, you can multiply those. What are you supposed to do? Add the exponents. Good. Right, you're right. So you get x to the 8th. Okay, everybody knows that. Good. Do you know when you have x to the 5th over x cubed, now you're dividing like bases, what do? Subtract the exponents. So you go 5 minus 3 and you're left with x squared. Yeah. I just shared another one with you. Like if you have x cubed raised to the 5th, this is when you have exponents raised to exponents. You multiply the exponents and you get x to the 15th. These are just, I'm reminding you, these are basic rules of exponents. If you have an x to the negative 5th, that means 1 over x to the 5th. We've talked about that one a lot, all right, already. Let me just prove to you this x to the 0 thing. Watch this. So we said if it's, watch this. So if I have x to the 5th over x to the 5th, now hang on a second. First of all, one way to think of this is, hey, it's some number over itself. Any number over itself is 1. So that's true fact. Nobody will argue with me, I don't think. But the other way to think is, what if you used your rules of exponents? You would subtract 5 minus 5, and what would you get if you subtracted 5 minus 5? X to the 0. So that proves to you, that's proof, that anything to the 0 is a 1. In case you needed convincing, in case you weren't convinced. These are pretty good notes. Listen, here's the thing, you guys. We've been messing around with a big pile of different exponential functions with different bases. Base 2, base 5, base 3. Here's the thing. There's one super famous base. It is this famous number that you may not have heard of before. It's called E. E is a famous number in nature. It's a famous number in nature. It is E. It is just a number. It is 2.71828, blah, 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 blah. It's one of those famous numbers that goes on forever. It's an irrational number. Its decimal goes on forever. We represent that number with the letter E. Can you think of any other famous numbers in nature that you do that with? Pi. Yeah, thank you. Pi is a famous number in nature, and we represent it with the symbol pi. By the way, the square root of 2 is also sort of like that. The square root of 2 is in here 1.414, blah, 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 blah. We usually represent it with the square root of 2. We don't have a letter for it, but we call it the square root of 2. But E is this famous number in nature, and it serves as a good base for exponential functions. And I know it's a weird number, but it serves so all these things I've been drawing are called exponential functions. This is called the exponential function. And it is this. The exponential function is y equals e to the x. And when you see that, it's new to you, it's kind of weird, but please think of e as a number. And think of it as a 2.7 if you want to, or just round it and sort of think of it as a 3. I mean, if you want to, think of it as a 3. Think of it as a, if you do some calculations, don't call it a 3. It's not a 3. It's a 2.718. It's a number called e. But just roughly, you thought of it as a 3. I mean, if you drew his graph, watch again. Plug in a 0. What's e to the 0? What's anything to the 0? 1. So what's e to the 0? 1. A 1. Is it growth or decay? Growth. Because e is 2.7, so it's bigger than 1. So when it's bigger than, it's about a 3. Roughly, it's about a 3. So it's exponential growth. And it's got this asymptote here, and it's good old x. Here it is. He looks like everybody else. He looks like 2 to the x. He looks like 3 to the x. But he's e to the x. Cool. So this is a whole category of things called exponential functions. But now we kind of narrowed, we've looked at 2 to the x, 5 to the x, 3 to the x. We're looking at all these guys. Now it kind of comes down to e to the x. That's kind of our buddy. I could really I could just talk about e to the x. What if I wrote e to the negative x? What would that look like if I put a negative up there? That would be decay. That would be this other version, right? Just that negative sign up there would make it decay. That's all. Watch this. I'm going to try something. This is sort of, I like this question. I want to graph this, and I want to graph this. Y equals 4e to the 2x minus 7. All right, I'm really messing with you now. I really stepped this up a notch here. Main reason I stepped it up a notch is because I put that damn minus 7 on the end of this. But you know, from being in this class, when I put a minus 7 on the end of any function, what does that do to it? Nope. When it's on the end, when it's a minus 7 on the end, what does that do? Shifts it No. It shifts it down. When you have a function and when you add a number on the end, that shifts it up. When you subtract a number on the end, that shifts it down. Shifting left to right was kind of weird. That was when you put it in the x, like a little x minus 3 in parentheses in the function. That shifted it to the right or left. X minus 3 was to the right. X plus 3 was to the left. Are you following me? I don't think I'm going to do much of that, okay? But I did shift this down. I put that minus 7 on here. Listen, that's kind of a big deal. I've been teaching you about this asymptote. I've been teaching you about this y-intercept. And now all of a sudden I shift the whole damn thing down. So I'm messing with you. I mean, I'm not messing with you, but I'm trying to challenge you got to think about this. It's different now. It's different than all the other problems I've done. Everything's shifted down. And I would say, focus on that shift. And I would say, take that asymptote that's normally right there at 0 and shift it down. So where is it now? It is, right. So at y equals negative 7, there is an asymptote. And then it's really not hard to find the y-intercept. You don't have to think about shifting. How do you always find a y-intercept? Plug in 0 for x. And you can do that, you guys. If you let x equal 0, you get e to the 0. You get 4 e to the 0 minus 7. That's just so easy to do. What's e to the 0? 1. 1 times 4 is 4. 4 minus 7 is negative 3. The y-intercept has been shifted down, and now it's at negative 3. Are you okay? Mason? I don't know. I didn't need shifts. I could have. Anyway, I can plug in a 0 and I can get the y-intercept. It's not hard. So I got my asymptote. My y-intercept is now negative 3. Dude, I got one more question. Is it growth or decay?
It's growth.
Okay, then you're done. Draw it. Phew! Or fee, or however you want to pronounce it. It's growth. There it is, baby. The key, I mean, this is good, you guys. This is good stuff. This is a test question. The key is it was shifted down 7. Shift down 7. I mean, I was teaching how to graph a bunch of these guys without shifting them. And now I just decided to shift one of them down. Not a big deal, but I'm not really going to get more complicated than that. That's good enough. Check this out, though. There's a lesson here. There is a lesson here. You know, when I ask you to graph something, I usually ask about 1 million questions. I ask, what's the domain? What's the range? What's the x-intercept? What's the y-intercept? Oh, what's the asymptote? What's the horizontal asymptote? These are all good questions. You ready? Let's try some of it. I mean, we already answered some of this, I guess. Let's start up here, though. Domain. I mean, I already got it all graphed. Do you know the domain? It spreads out over all x's. It is, yes, negative infinity to infinity. Do you know the range? Can you see the range after we graphed it? Good. You know, back here the range was greater than 0 because it never went below 0. But now that it was shifted down, now the range is greater than negative 7. Right, the range is the y values greater than negative 7. So the range is y greater than negative 7. Is that okay with you?
Yes.
I'm asking for the horizontal asymptote, which again has to do with the shifting down 7. I mean, normally the horizontal asymptote is called y equals 0, but this one was shifted down 7, so it's y equals, it's that line called y equals -7. That's the name of the asymptote. It's a line. Hey, a few minutes ago I asked you for the x-intercept. Go back to this picture. What's the x-intercept on this picture?
None.
There is none, right? It never, because of that, right. But now that I shifted it down, is there an x-intercept? There is. And finding that's going to be a little tricky. Let's skip that a second. The y-intercept. We already got it. How do you get a y-intercept? You plug in a 0 and you get -3. Right, you guys? Okay. Listen, I want to talk about that y-intercept just a different way. A few minutes ago, over there in my notes, watch this now. Take the 7 off for a second. What would be the y-intercept? You could plug in a 0 and tell me. Plug in a 0. What's the y-intercept? 4. Or if you looked at my notes, this number in front of the base is e in this problem, but the number in front of the base is the y-intercept, is what my notes say. But not when it gets shifted down. So the y-intercept was 4. When it got shifted down 7, so it was 4. When it got shifted down 7, it ended up at -3. Very logical, if you want to think about it like that.
So you just subtracted 4 -7, get -3.
Well, right, and I did that when I plugged in my 0. I ended up 4 - 7. I don't know, I just wanted to say my notes over here said that this is the y-intercept, but this one doesn't follow my notes. Why not?
Because of -7.
Because of the damn -7. Thank you. It's been shifted down. It's a little different than my notes. Right. Right. So now, here comes the kicker. You ready? This is it, man. This is the key. I want to find that x-intercept. I want to find that x-intercept. And if I want to find an x-intercept, how do I always find an x-intercept? I plug in a 0 for y, and I have to solve for x. I have to solve for x. And this is when I got to, well, you could start. Why? But you're not going to be able to finish until I help you. But you could start. If you're trying to solve for x, what would you do? Add 7. She says add 7. Okay, I like that. You're trying to get x by itself. What would you do next? I would divide by 4. I would divide by 4. If you divide by 4, it cancels over here. You get e to the 2x equals 7/4. But now you're in this situation where you want to get x and you want to get rid of that base e. And you don't have any algebra skills to do that yet until I teach you the last great algebra skill. I need to inverse the e function. I need to do the inverse of the e function. Remember Tuesday we talked all about inverse functions? They undo each other, right? They undo each other. Well, the inverse of an e function is a logarithm. And specifically, there's all kinds of logarithms, but when it's base e, then we do use what's called the natural logarithm. Now, I need to give you a lecture on what the natural logarithm is, but I kind of don't. To solve this equation, I just need to tell you that the inverse of e, the way you kill an e, is you take the natural log of both sides. It's a step. It's like kind of taking the square root of both sides, or adding 4 to both sides, or dividing by 7. It's an algebraic step called take the natural log of both sides. The natural log is represented with this ln. So here I go. I'm taking the natural log of the 7/4. I'm sorry, I'm moving up here, you guys. I'm taking the natural log of the 7/4, and then on the other side, I'm taking the natural log of the e to the 2x. But the big idea that you're just now getting introduced to is that natural log and e are inverses of each other. So they cancel each other. Thank you. They just cancel each other, and what am I left with?
2x.
2x, and it's not up in the air anymore. Now it's down here. It's at 2x.
So you divide by 2.
Well, hold on. You're right. Now I got one. Now, yeah. You catch that step? The step was called take the natural log of both sides. Why? Because natural log will kill the e. Will cancel the e. And I haven't really explained why yet, so you'll believe me. You trust me, I think. But it's the inverse of the e function. The natural log is the inverse of the e function. I haven't told you all that big background story. There's a big story behind that. But you almost don't need that story. You just need, to solve for x, you just need to know that to kill an e, you need an ln on both sides. Listen, some students look at that move right there and they say, oh yeah, I get it. He multiplied by an ln. That pisses me off. I mean, it's not multiplication. I'm sorry. I'm not multiplying by an ln. That's not what I'm doing. You know, look at this. When I have x squared equals 9 and I take a square root, am I multiplying by a square root?
No.
No, I'm not. No, I'm square rooting both sides. So I'm logarithming both sides. It's not multiplication. It's just taking the log of both sides. And the purpose is that it does kill the e, gets the x down. It's actually a 2x, so there is one more move. She said it a long time ago. Divide by 2. Thank you. And so x is this natural log of 7/4 divided by 2. And that's the answer. That's the x-intercept. Listen, we need calculators. This is where we finally need, well, we've always been able to use calculators, but now we kind of need our calculators that have E buttons maybe, E buttons, or log buttons. Now I'm looking for you to try to find your ln button. And can you do the ln of 7/4? It's a decimal. And can you divide by 2? Everybody should sort of practice this, or at least if you don't have it today, go home and practice using your calculator.
0.279.
That's the final answer?
Yes.
He did the natural log of this number, whatever he got, he divided by 2, and his final answer is 0.279. Do you guys agree?
Yeah.
Okay.
You want us to round it?
We are going to have to round it, and I do kind of like to round it to 3 decimal places. That's sort of my habit with logarithms.
So 8.
So is 279 a good rounding? What was the next number?
8.
The next number was an 8.
Yeah.
That means I got to round this up.
280.
So 280. Okay, if I'm really rounding to 3 decimals, okay, we better do it correct. 280. All right, cool. That's awesome. That's awesome. That's a cool lesson, you guys. How do you solve an exponential equation? You use logarithms. Not right off the bat. First you move the 7 over, you divide by 4, you expose that base e. How do you kill a base e? You use logarithms. Logarithms undo an e. So that's that little x-intercept right there. Here, I'll just put my answer. If I put my answer up here, what should I put? The exact answer? Natural log of 7/4 divided by 2. That's the exact answer. What's the approximate answer? 0.280. Thank you. And on this graph, that's where that is, roughly 0.280.
So how would you want us to answer on the test, like that, or do you want decimal?
Both. I don't mind. I like to see your work. I like to see you do this. I like to see you pick up a calculator. I like to see both, kind of. Yeah. Okay, listen. So I'm still in 5.2, but when I brought up these logarithms, I sort of was moving into 5.3. But I'm not yet. I'm not moving into 5.3 yet. But 5.3 and 5.4, I'll teach you about logarithms. I'll do it quickly. But I tell you what, there's a lot of value in what I just did. I mean, you can almost not even understand logarithms, but use them. You can use them for your purposes here. To me, the main purpose of logarithms is to help you solve exponential equations. We had to solve this exponential equation to find the x-intercept. Now, before I leave 5.2, there's more stuff in 5.2. Listen, one of the reasons we love these functions and study these functions is things in the real world do this. They do grow exponentially. I mean, you know, maybe back in chapter 1 I told you, oh, things grow linearly. Well, I was lying. Things don't grow linearly. No, actually, some things might grow linearly, like a line. But actually, a lot of things grow exponentially. Populations, the way animals breed, and you know how that works, right? Anyway, populations grow exponentially. Populations grow exponentially. Money deposited in a bank earning a certain interest grows exponentially. It's got that bend to it. It's got that curve to it. Things die and depreciate. They decay exponentially. They decay with that curve. I mean, things in real life act like this. And so we study this. And so some good word problems are some good money interest problems. And so I want to teach you about this formula. A equals P 1 plus R over N raised to the NT. This is a classic formula for compounding interest. Compounding interest. N times per year. N times per year. So I put some money in the bank, and the bank pays me interest. And they sort of pay it to me in this funny way. They compound my interest a certain number of times per year. N times per year. Let's talk a little more about this. So the capital A is kind of like the final amount of money that it grows to. I put some initial amount of money in. Guess what the initial amount of money is?
Principal.
That's the P, that's principal. We call that principal. That's the initial amount of money. And then it's going to grow, and it's going to exponentiate, and it's going to grow to this final answer. So A is sort of the final amount of money. Final amount of money. P is the original amount of money. The word is principal. Principal is the starting value, original amount of money, and I can say it a lot of ways. The original amount, the initial amount is a good way to talk. Let's see, the little r is the interest rate. You know, they're going to pay me a certain interest rate. Nowadays, interest rates are low. They don't pay me much, 1%, 2%. 3%, they give me some kind of an interest rate. When they give me an interest rate, it's per year. It's a yearly rate. It's an annual rate. Therefore, the T is the time, and therefore the time has to be in years. Okay, so that means this is like I put my money in the bank, my original amount of money, and I leave it there for 20 years. So the T is 20 years. You with me? It earns interest for 20 years. So time is in years, not in months. And then there's one more thing in this formula, and that's N. So N is kind of the weird thing. N is the number of times it's compounded per year. It's the number of times it's compounded per year. Now, I want to do a real problem. I want to do a real problem with you and show you how this works. It's not that hard. Are you guys okay? Any questions? But I kind of want to do this problem orally here a second. Just hang on, bear with me here. If I can do it without writing anything on the board. All right, hold on. So I start off with $100. I want to put $100 in the bank. Let's say the bank pays me 12% interest. 12% interest. That's a lot. They don't do that anymore. Back in the 70s and 80s, they might have done that. But anyway, they pay me 12% interest. And listen to this, they compound it once a year. So what that kind of means is I put my $100 in the bank, and I got to sit there and I got to wait a whole year really before it even earns any interest. And then when it comes back on my 1 year anniversary, they say, okay, it's time to compound his interest, time to pay him his interest. And so they pay me 12%. So they pay me 12% of $100. So what did they pay me? $12. And so now I have $112. Hang on, I will write that down. So now I have $112, and now a whole year goes by before they do it again. But after that year goes by, now they pay me 12%, but now it's 12% of $112. What is 12% of $112? You need a calculator.
Well, if you can, it'll add up to 125.44.
Okay, what was the 12%?
I just multiplied by 1.12.
Okay, that's kind of smart. Can you tell me what the 12% is?
Okay. 13 hours and
1344?
Yeah.
And he had it already added. So this was my interest the second year. What was my interest the first year? $12, right? And so what was my interest I earned the second year? $13.44. You know why it's more? Well, I had more money in there. And the reason I had more money in there is because the interest I earned the first year. See, this is where the word compounding comes in. My interest earned interest. Are you with me? I think that's where the word compounding comes in. My interest starts earning interest in the subsequent years. So anyway, I get more money. And now I have a total of this. And then I can do it again the next year. I mean, are you following me? Okay, hold on. So this was after 2 years. This was after 1 year. Okay. All right, let's do this different. Watch this, watch this. Let's do it different. Almost the same thing though. $100 I put in the bank. They're going to pay me 12% interest. Same thing, except this time they do this thing where they compound it monthly. So that means I put my money in there and I only got to wait a month before they give me my interest. Now hold on. So they give me 12% interest, but that's a yearly figure. Hold on. That 12% interest is a yearly figure. They got to give me 1 month's worth. What's 1 month's worth? They divide by 12, so they give me 1% every month. 12% per year. They divide by 12, and they're going to give me 1% for that month. Okay, so what's 1% of $100? $1? Okay, so they give me $1. So now I got $101. That's at the end of the first month. Then another month goes by, and they give me 1% again. So that's $1 and a penny. I think that's $1 and a penny. Then another month goes by, and they give me another 1%. And anyway, what if we did that for 12 months? Now I kind of need the formula. If I did that for 12 months, I'd have my $100. I'd have my, watch this, my 12% interest divided by n. And since, when I said the words compounded monthly, n is the number of times per year, so n is 12. So you divide by 12, and then in 1 year, how many, you're going to do that 12 times for 1 year. So you're going to do that 12 times. So you with me? 12 times 1. I'm trying to sort of explain the formula, how it works, but I'm also just trying to do this. So now I'd like to do this. When you divide, that's your 1%. When you add it to the 1, that's 1.01. That's you earning 1% every month for 12 months. That's what that is. Multiplied by the initial 100, what do we get? Again, now you need a calculator. And you need to know how to go 1.01 raised to the 12th. You need a good calculator, know how to use it. And then you need to multiply by 100.
It's $112.68.
$112.68. Thank you. That was a long little oral problem there, but did you catch it? What was the deal? When you compounded once a year, what did you get? $112. When you compounded it monthly, that little bit of pennies and dollars that you earned earlier in the year added up to an extra 68 cents. By compounding it more often, by them paying me a little earlier, that interest got to earn interest. Okay, let's do a real problem. I put $5,000 in the bank. I put $5,000 in the bank. problem is, how do you ever get $5,000? But anyway, if you ever get it, put it in the bank. They pay me in the bank. They pay, I'm going to say they pay 8% interest, compounded. That's another option. I can do this thing compounded quarterly. By the way, I can do it daily, quarterly, monthly, yearly. I guess I can do it bi-monthly or bi-yearly. I don't even know what that means. But semi-monthly, that's twice a month. Bi-monthly is every 2 months, I think. Okay, anyway. Quarterly. Quarterly is every quarter of a year, and a quarter of a year is every 3 months. But how many times a year is that? That's 4 times a year. So what's n? When you read these words, it's up to you to decide n is 4. Right. Good. When you read the words compounded monthly, n is 12. If you read the words compounded daily, n is 365. All right, now how long do I do this? Let's leave it in there. I leave it in the bank. That's the other thing I got to tell you. I leave it in for
1 year.
Let's leave it in for 20 years. I mean, that's what you're supposed to do when you save money. You're supposed to forget about it. Watch it grow. I mean, I don't know. I don't do a good job of saving money. I never have, but none of us do usually. But if you're trained to save money, you're in a better shape maybe. Here I go. I'm putting in my $5,000 principal. I'm going to use this formula, by the way, you guys. Here I go. 1 plus R. What is R?
8%.
R is the 8% interest rate. Listen, when you use this formula, you got to make it a decimal. Like I did with the 12% interest rate, I called it a 0.12. With the 8% interest rate, I got to call it 0.08. That's important. Don't call it a 0.8. That ruins it. It's a 0.08. All divided by what? N? What's N?
4.
Oh, N is 4. And then it's raised to the N times T, because it's 4 times a year for 20 years. So you're going to do this 4 times for 20 years. You're going to do this 80 times. Your exponent is 80. You following me? What I would do is I would divide this and add it to 1, and that's your base. What is that, please? 1.02? So that's your base. You're raising it to the 80th. You need a calculator to help you. And when you're done with that, please multiply by 5,000. Do not multiply the 5,000 in there. That ruins your answer. This is cool. This will be a bunch of money, I think. $5,000, 8% interest for 20 years, compounded quarterly.
It's $24,377.20 rounded.
Okay, good. Thank you. In these problems, he did that correctly. It is dollars and cents, so we should round to 2 decimal places to get our cents correct. And so what did he say? What did you say?
20 cents.
20 cents. You guys, now that's good. Now, you should be picking up your calculator and practicing these moves here. I mean, it came down to this move is what it came down to. These aren't really too hard. And by the way, I think I'll give you this formula. I won't make you memorize it. But I won't give you all this. So you do kind of got to know what's what. You got to practice using the formula and knowing what's what. But I think I'll just give you the formula. That's pretty cool, man. You know, the problem is 20 years from now, $24,000 ain't what it used to be. Inflation sort of eats it up. I mean, it's not what it used to be.
Only 3%.
Well, you're right. Inflation tends to be 2 or 3% every year. So when you think you're earning 8% interest, if inflation's eating up 3% of that, you're really only earning 5% interest, which is still something, but yeah, there's sort of a reality sets in, kind of, right? But, you know, compounded quarterly is every 3 months. Is that Yeah, every 3 months. So if I did it compounded monthly, what would you think? That would be every month. It would be, we'd get more money, I think, because our interest would start earning interest more often and we'd get more money. The truth is, it won't be that much more. I mean, we would wait 20 years and it really wouldn't be that much more. When you go from quarterly to monthly, or even, let's go to daily. Let's just do it daily for a second. No, let's not. Hang on, let's not. I don't want to bother. What I really want to do is this. I want to show you this other formula. Listen to this. So if you compound it quarterly, n is 4. Okay. If we did it more often, if we compound it monthly, n is, please tell me, 12. If we compound monthly. If we did it daily, n would be 365. But every day the interest is so small. You know, it's a day's worth of interest. It's very small. But you would do it every day for 20 years. Okay, listen to this. You can do it continuously. Continuously is more often than daily. Continuously is like every hour. No, it's not. It's like every minute. No. It's like every second.
Every time it's traded.
No, it's like every half a second. It's continuously. So hang on. What just happened to n? How many? If you're doing it every split second, how many n's? How many often is that in a year? Infinity. Dude, you're right. Listen, if you compound continuously, n goes to infinity, which is kind of a calculus concept, but it's not that hard of a concept. N gets huge, it goes to infinity, and if n goes to infinity, this formula changes to this formula. E to the RT. We end up with our base E that we talked about earlier. And look, notice something. There is no n in the formula. The n goes away. The n went to infinity, and you don't have n anymore because you're compounded. You're not compounding certain times per year. You're compounding continuously. I like these better, and this is really easier to work with than that formula. So this is not supposed to be harder or more advanced, but it's just different. It's just another option. So let's do this problem. What if this guy did it compounded continuously? Here we go. He would have $5,000. E, the number E, raised to the R. What's R? 0.08. That's the interest rate. Times the number of years. What's the number of years? That's T. T's the number of years. 20 years. So you got to multiply that. You got to E it. Then you got to multiply by your 5,000. There is no N. To me, it's an easier formula, but you got to find your E button and know how to use your E button. Usually your E button is on a calculator. It looks like this. And when you type it, when you hit that button, it's waiting for you to type in the exponent. Here, hang on. What is the exponent? What is 0.08 times 20? I don't think that's right. Hang on. 0.08 times 20? 1.6. Now maybe that's, okay, so then when you E the 1.6, that was your 4 point something. When you multiply by, okay, what's this answer, please?
It's 4.95.
Okay, what'd you say? 24,000.
765 and 16 cents.
Okay, you guys agree?
Yep.
It's cool if you have your calculators and you can practice. You can double check yourself here and see if you're getting this. You got to find your E button. If you don't have an E button, what could you do? What is E? 2.71828. So if you don't have an E button, I guess you could use that try to use that number. But you might be a little off because you're rounding it off. It's cool to use your E button. E to the X button. You should have an E to the X button, I think. Anyway, so guess what? Look how much, in 20 years I got what, $400 more? Look. In 20 years, it amounts to $400. I mean, it's $400, but it's not that much better, right? What was this? This was compounded quarterly, and this was compounded every split second. Wow, it's not that big a deal.
you're trading in millions or billions, then it means something.
Well, there you go. You're right. You're right. A lot of things, right. Change the $5,000 to millions or billions, and you're exactly right. Change that interest rate a little bit, 9 or 10%, 12%, and yeah. So a lot of little variables can affect that. You're right. You're right. All right, you guys, I got a question for you. This is good stuff. This is all in 5.2. But when I ask you this next question, it kind of takes you into 5.3, 5.4, maybe 5.5 actually. But here's this next question. We're talking about this compounded continuously, and I want to know this question. You ready? When will I have $1 million? Do you know who that was? That was Dr. Evil. That was a great Dr. Evil impression, don't you think? You guys don't even know who Dr. Evil is. Was it? Then you would know it was a terrible Dr. Evil impression. When will I have $1 million? So what do I do? I plug that in for the amount, the final amount. Good. And what I'm looking for is when, which would be what? The t. So I'm looking for the time when it's $1 million. So how does this, right, so you're right. I'm going to plug in the million right here. Here we go. I'm plugging in the million right here. That's 1 million. Equals the 5,000. E raised to the 0.08. Is that right? This is still this problem with 0.08. And then I don't know t. So I got this unknown t. And I want to solve for t. And we learned how to do this without really understanding logarithms, but we learned that to solve for t earlier today, we use a logarithm. I didn't really teach you what logarithms were, but I taught you what they're used for. If I can do this, you guys. I can, what would you do first? Divide by 5,000. That's totally true. And I've seen weird students subtract. It's totally bad. You divide by 5,000, of course. You divide by 5,000, of course. That does expose the e, so you got to get that e exposed before you can kill it. It's like hiding behind the bushes. Now you can kill it. What is this over here?
200?
200?
That's what I got, but I think I'm wrong.
I don't know if that's right.
I think, let's see, if I cancel 3 zeros, then I got 1,000 divided by 5. 1,000 divided by 5 is 200. Okay. Now what do I do? To kill the e, you do this step called take the natural log of both sides. So you get the ln of 200 and you get the ln of e to the 0.08t. The purpose of that is that ln and e are inverse functions of each other and they cancel each other. So they're gone. And so you have that 0.08t down here on this line, and you really only have one more move if you want to solve for t. Divide by 0.08. Following me? You do this move called ln both sides. Why do you're trying to get this t down, and you got to kill its base. And this is a new concept. I mean, this is a new concept. How do you kill a base? You use logarithms. And I haven't even taught you what logarithms are, but I've taught you what they're used for, to kill the base and help you solve exponential equations. That's what they're used for. So when I take the ln of both sides, it kills the e, you get this down, you get this number. This is a number on your calculator, you guys. And anyway, I got one more move to get t. Divide by 0.08. The answer is the ln of 200 divided by 0.08. It's probably 50, 60, 80 years. I don't know. What is it?
66.23.
Good, thank you. You did this on your calculator, and it came out to 66.3? 23? 66.2 years. What'd you say?
The ln button should be right with the...
It might be the second of the E button, or the E button's the second of the LN button.
Yeah. The E button should be
They're together, kind of, and you have to hit second, maybe. That's true. That's awesome, you guys. Hey, thanks for listening. Where are you? Do some homework. 2, 3, 5, 1, 5, 2. You really probably can't do much of 5, 3 yet. Yes, ma'am.
That 1 million after 66 years, is that with an initial investment of 5,000?
Yes, ma'am.